Hello, Arjuna.
Hi.
Yeah.
Yeah. Can you hear me
Uh,
now?
yeah. Can you
Yeah.
can you start up your presentation while I introduce your bio?
Yep.
Yeah. So our next speaker is Dr. Arjuna Flanner. He received his PhD in mathematical physics from the University of Missouri Columbia in 2014, and then he worked as a postdoc at the Naval Air Weapons Station in China Lake, California, and then he became a research scientist at the same location. So during his tenure at Navia, he developed a machine learning, image processing, and signal processing algorithm for a variety of systems, where he became the lead scientist on the machine intelligence and learning initiative. So his research interests include new machine learning, statistical pattern recognition, image processing, and computer vision algorithms for Navy applications. And this research has resulted in over 30 papers in the open literature and led him to oversee the transition of machine learning into multiple naval systems. So in 2014, he received the award Dolores Atter Award as one of the Navy's top scientists, and his graph theory work on using PDE methods to solving novel graph problems has won the SIAM Best Paper Award and SIAM Digest Award. Okay, so now, Adrina, please start your talk.
All right. Thank you. Thanks for the kind introduction. Like I said, I'm Arjuna Flanner with GE Aviation Systems. Patrick Carroll will be joining me on this talk today. We're going to split it into two parts. Patrick is really the PI on this project. So he's going to stand introduce, and I'm going to talk about some details on how we're trying to actually optimize some of our. All right. So let me go to the second slide, and hopefully Patrick can join us.
Yeah, I'm here. Just want to do a quick mic check and make sure I'm coming through.
I can hear you.
Okay, great. Okay, great. Yeah, so thanks for having us. So I see it. We're up on the screen here. So again, to Arjuna mentioned, we're from GE Aviation. We're in the avionics group within aviation, and we're stationed in Grand Rapids, Michigan. So this briefing is going to be centered around, how do we enable autonomous UAV operations, but do it, you want to think through the practical constraints and limitations with doing that, and try to bridge the gap between R&D, academia, and real life scenarios. So if we break down, how do we do that? What are the requirements to do that? We really have to think about a couple different things. First, we need an algorithm that dynamically optimizes our waveforms in real time. But that algorithm then needs to reside on a platform that can process that in real time. So you need enough computational horsepower to do that, while at the same time taking into account the operational or payload constraints. And the other aspect to think through is, how does this optimization algorithm work with real world and increasingly complex RF signals? So what we use as kind of a starting foundational point is the Hornets algorithm, which some of you on the call are probably familiar with, but we'll go into what that is. But what we've done is use that as a novel starting approach, and we built an additional objective function on top of that. And what we found is that when you combine these different objection functions, we can see improved results. So just to give you a little preview, if you see the figure on the bottom left of the screen, you have a complex RF input that goes through this optimization algorithm, and then ideally you have an orthogonal waveform that comes out of that kind of bends around the signal space. So let's go to the next slide, and we can kind of get into the meat of the presentation. And if you think about the fundamental, mission that we're trying to accomplish here, and as we go to the next slide, Arjuna, it consists of, autonomously maximizing network throughput in real time, on a distributed set of nodes. So at GE Aviation, it shouldn't come to surprise anyone that we like to put things in the air, right? That's our jam. That's what we like to do. So of a particular use case that's interesting to us is, how do we have uninterrupted communications and data routing between UAVs that are executing a mission in a challenging RF environment? So to be able to do this, we need a dynamic algorithm that optimizes RF waveform in time. So a novel candidate for that is the Hornets algorithm, which is the autonomous interference avoiding networking solution. So we're not going to claim credit to that. We have a partnership with Florida Atlantic University, University of Buffalo, and the Air Force. And Arjuna, when we go to his section, he's going to talk more through some of the mathematical construct of the algorithm. But just to give you a high-level approach of what this is, the concept is that Hornets essentially leverages back pressure routing, where you can direct traffic through a queuing network to maximize throughput. But it takes on the difficult challenge of doing this in an infrastructureless way. So another way, you have these disparate nodes. In our case, you have UAVs. So what it does is essentially maximizes spectral efficiency by optimizing both the waveform and the routes in a multi-hop network. And I don't know if you can see the slides there. It seems to kind of drop off, but I'll continue going. Maybe Arjuna is able to hop on if he's having some technical difficulties. But if we have a candidate, use case, right? That's why you want to enable autonomous UAV operations. And we also have a candidate approach, which is the Hornets algorithm. We need to start thinking about the hardware, the different constraints, right? So at GE, we consider ourselves to be experts in industrializing technology. So always at the forefront of our mind is, how do we do that? How do we bridge the gap between academia and actually putting something in the field that is usable in the real world? And so one of those operational considerations is hardware. So you have a candidate, an algorithm, for example, candidate waveform solution, but you have to be able to put that on a piece of hardware. And there's a trade-off between your solution and the execution time and the fieldability of the hardware itself, especially if you consider the fact that, in many cases you want to put something in a small UAV. There's extreme payload restrictions when doing so. So I'll introduce, I'll give a pitch to one of our products. It's called the M100. There may be a handful of you on the call that are familiar with that product. But essentially the M100 is part of, and I don't know if, let's see, maybe Arjuna will be able to get back on and share. We have some pictures of the hardware. But I'll keep talking through. It's 2020, so we'll keep powering through.
Wait.
Arjuna, you there? We'll keep going.
Can you not see that?
It might just be me. So so the M100 is like I said, it's the smallest of what we call the M series. It's a suite of our advanced avionics mission compute system. It's only about 1.5 pounds, and its form factor is about 6.5 by 3 by 1.5 inches. But it has the computational horsepower to do a lot of things. So it has the flexibility. So it has onboard sensor processing, has a software-defined radio, configurable communications. But it also, like I said, has the horsepower to to provide autonomy at the edge. So I like to think about it as a Swiss Army knife with wings, essentially. And fortunately, through our partnership with Florida Atlantic University, we were able to show proof of concept that we can actually port this algorithm onto the M100. So we think we have the basis covered for the hardware considerations. So if you want to swing to the next slide, another consideration that we have to think through is the RF consideration. How does the algorithm you choose actually respond to the RF environment? So as we're entering 2021, and I'm sure most people, including myself, are happy to be turning the page on 2020. We're seeing an explosion and a surge of devices using wireless technology. And so what that means is that we have a very congested RF spectrum.
Hello, Patrick. So we still cannot see the slides.
Yeah, let's see, maybe if I share, looks like maybe Arjuna, are you sharing your slides?
Yeah, it says I'm sharing my screen. So let me just try again.
Yeah, just try stop the sharing and then reshare again.
Can you see it yet?
No. Maybe refresh the web page.
Okay.
Maybe I should try to share my screen. I might have a better connection.
Yeah, if that works.
Is this working now? We got it?
Yeah.
All right, thanks.
Great.
Okay, well, as I mentioned, I think we have a picture of the M100 up here, so I'll just scroll through that real quickly. That's the actual M100 in its visual glory. But if we look at, we talk about the RF considerations as well. As we're having more and more of a complex RF environment and congested RF environment. But if you think of it from an EW perspective, it's even, you think about it as a worst case scenario where you have potentially these adversarial systems which are trying to break your comms and data links. And so what we've done is we developed a modeling tool, create synthetic RF data, and then really test the Hornets algorithm and see, okay, if we put multiple sinusoidal tones or multiple carriers and increase the noise floor, what does that do? What are the practical limitations of this algorithm, and how can we maybe build upon that? So with that being said, let me turn it over to Arjuna, who can talk some of the math behind the approach and the new objective function.
All right, thanks, Pat. And so, like Pat said, we've been working with Buffalo and Florida Atlantic University on the Hornets Waveform. So here I present the Hornets Waveform. So we were really trying to transmit information using B with a carrier waveform here. And the goal here is to design this carrier waveform so we can optimize our transmission through the spectrum, through the frequency. So to do this, we got to consider psi of t, how we're going to generate psi of t. We are assuming S are the coefficients of translates of a square root raised cosine function, and S is constrained to take on two different values. And then L is our second important parameter. L really tells us how many different waveforms are possible in our generation. And with a higher L's, we can exploit, we have more choices, or we can adapt to more different environments, right? So given all this, with the paper presented on the last page, there is a general strategy here to generate these waveforms, to determine optimal waveforms, and that is to maximize the signal to interference plus noise ratio, which we look at the autocorrelation function of the noise, right? So this optimization problem, given here in the bottom, is all except for this constraint on S is really finding the first eigenvector of the inverse of this matrix, right? So with this constraint, however, it makes the problem much more difficult to solve. I understand as this is more, and that's this eigenvector method, which is really just a relaxed version where we really determine the quantized values there, right? And then there's a single bit flip method, which really asks the question, if we change one value of S, how does it change the objective function? And if that changes sign, then we can, actually, if it goes negative in the change, then that bit is a valid bit to be flipped, right? So our method, I'm really motivated by work I did on graph segmentation, or machine learning type method. There's diffuse interface models and graphs. So what it really does is kind of interpolates between these two ideas, right? So the first thing we do is we modify the objective function, but with this normalization constraint, the objective function L here is really pretty much the same as the previous objective function. However, normalize it for computational considerations, right? And then we have a second part of the complete objective function, which is a double well potential. This is forcing our values to take on this plus or minus 1 over the square root of L, right? So it's a double well where the 2 minimum of the well is plus square root of L, right? So why do we think this might work? Well, the Ginzburg-Landau function has been used. It's called a phase field model, but it's known to be effective when there's multiple time scales, in our case, in this problem, right? So that means there's multiple different type of waveforms in the problem, right? I don't know why I did that. So we're conjecturing that this objective function will help that, right? So the way we look at these multiple time scales is this parameter epsilon. So as epsilon goes to 0, we're just a double well, and as epsilon gets large, we're just the original eigenvalue method, right? So, if you look at it, I don't know why it's doing that, but we have a PDE, our computations are really motivated by PDE theory, but don't be worried here. It's not much more difficult and much more computationally intensive than the single bit flipping method. So we did some examples to try and prove out that this method was appropriate. So what I have here is first I compared with L equals to 8. So this is a relatively simpler spectral environment that we're looking at, or potential number of waveforms we're looking at. But we can also compare it to the actual maximum objective function that we can achieve. So we can go these waveforms and find the best waveform possible and compare our value that we obtain with that. So with just one jammer present, these single pulse jammers, the Ginsburg-Landau method values are the method performs the worst. As we move up to a more and more complex space, the Ginsburg-Landau starts improving a little bit better. They're both still pretty close to the optimal type performance. We move away from optimal performance as it becomes more and more complex. And the last year, we are pushing the L value so we can no longer compare with optimal performance. And the Ginsburg-Landau better can start doing Ginsburg-Landau method starts doing better than the bit flip. However, the two methods are actually doing different things. They're looking at different aspects of the problem. So by combining them, we actually obtain even better value, right? So this is kind of our strategy. Oftentimes with NP hard problems is if you can start combining methods, you can actually get better results in the end. So that pretty much concludes our talks. GE Aviation, we're really interested in enabling these future autonomous vehicles. So we're building the hardware. We have vast experience in building flight-worthy and safe hardware. But we're also looking at teaming with academia, with labs, in order to enable our hardware to do these autonomous types of missions, right? And we're trying to push the envelope too on what. So with that, I'd like to thank you for inviting us again, and I can open up the floor to questions from Pat or I.
Okay, there is one question from the audience. How do you envision the role of wireless sensing in the future? Are power spectrum measurements enough for maximizing spectral access across heterogeneous technology, or will we be relying on a more robust standard of environmental awareness?
I hate to say this, my connection, as you guys may have noticed, is terrible. I can't hear the question. Can you hear what they're asking, Pat?
Yeah, I'm just, it was a little choppy, but so I think I see it here. Is how do you envision the role of wireless sensing in the future? That's the correct one, I believe. Our power spectral measurements enough for maximizing spectral access across heterogeneous technologies. We're relying on a more robust standard of environmental awareness. And I think some of our presenters hit on this a little bit earlier as well, is that, we have to think through, how do we share the spectrum ultimately? There's a sensing aspect, and then there's the sharing aspect. So if I understand the question correctly, how do we jointly share the spectrum when we have an increasing congested environment? And I think that's a great question. When you start to look at the approaches for spectral sensing, you look at cyclostationary features, for example. You do match filtering, there's energy detection, but a lot of those sensing elements require some knowledge of the waveform itself. So as we get into this more cognitive approach, we have to start looking into other models that we might have taken from other industries, such as image processing, deep learning, for example, to see if we can leverage spectrum sensing, which ultimately leads to spectral sharing, when we don't have good understanding of the actual signal space in general, as it becomes increasingly complex. So I don't know if you want to add anything to that, Arjuna.
Since I apologize, I can only hear half of what everybody's saying. So I think the answer must be great.
All right. Any other questions? All right. Let's thank the speaker, thank Patrick and Arjuna. Thank you.
Thank you.
Our next talk